Hi, this is Mr. Leach with Simpson Math. Today I will be talking about hypothesis tests and specifically the one proportion z-test along with errors in power. In a moment, you should pause the video and read the situation and questions on the screen. Then try to answer them to the best of your ability. When you've finished, hit play and I'll explain the solutions and my thought process. So go ahead, pause the video, and try this on your own. So to begin with, you should think about whether or not the data we have here is categorical or quantitative. So when you look at this, you see that most definitely it is categorical. We know this because we just have a yes or no situation, which means we're going to be dealing with proportions. The respondents of this survey will either say, sure, I'll pay $100 for the survey, or no, I won't. And since we're dealing with proportions, the population parameter is going to be P, and the sample statistic is going to be p hat, and the type of test we will run is a z. In my AP Statistics class, I teach my students a 4-step process to answering hypothesis test questions. I have them state, plan, do, and conclude. So here we have state. Our null hypothesis is that the population proportion is going to be equal to 0.2, and our alternative is going to be greater than 0.2. And we know that because it says more than 20%. And we got the 0.2 part from the 20% part. Our alpha level or our significance level is going to be 0.05. And the P is equal to the true proportion of customers who would pay $100 for the update. On the AP Statistics test, it's important that you have all three of these elements, especially your hypotheses and your parameter defined in context. Next, we have our plan step. So we have our random condition. So this is a random sample of 60 customers, so we're good to go there. Additionally, we know that the 10% condition is met because 60 is likely less than 10% of all the company's customers. This basically makes sure that independence is sound. This is because we are sampling without replacement. And as we can see here, our large counts condition is met. I tell my students that you have to have either of these mathy bits, either the math 60 times 0.2 or the number. You don't have to have both, but I show them both here for clarity. You do have to have the n times p or n times p null, depending upon how you want to write it, and you do have to have the greater than or equal to 10 part. This makes sure that our sample size is large enough. Since all three of these conditions are met, we can then do a one proportion z test. You need all four of those words there. Next, let's do the do step. So I went to the calculator and performed a one proportion z test. When you do this, it's going to ask you what's your p null, or just basically the value equal to the p, and well, that's just 0.2. It's going to ask you what the x is, and we see that that's 16 from the stem of the question. It's going to ask you your sample size you're in, and that's 60 also in the stem of the question. And then it's going to have you confirm your alternative hypothesis and make sure to change it to say that it is greater than. So that way it's p is greater than 0.2. When you run the test, you see we get a z of 1.29, a p-value of about 0.098, a p hat, that's our sample proportion, is 0.2667. We got that from doing the 16 over 60, and then our sample size is 60. Along with these calculations, you should also draw a graph. That tells me or the reader that you know what you're doing other than just what the calculator spit out. So we have our value from the null hypothesis, the hypothesized p at 0.2 in the middle of this normal model. And then our p hat, the 16 over 60, which is the 0.26666 forever. And if we find the area greater than that, that is the 0.098 or 9.8%. So for the AP test, this is all that you need. You just need to write down what the calculator gives you, and you need to draw the graph. Secondly, though, it's a good idea for you to understand the math. They could ask on a free response question with very specific directions for you to show all of your work, but that's not very likely. They're more than likely to assess this on a multiple choice question. So it's a good idea to make sure we know where the z and the p-value came from. So our z came from this formula, p hat minus p null over the square root of p times 1 minus p over n. And so if we substitute all those values in, we get 1.29. Now, how do I know all those things? Well, if our p hat minus p null, that's just our observed minus expected, just like we learned z way back in the day, and it's just divided by standard deviation. And the standard deviation is the same standard deviation you learned back when you learned about sampling distributions, and it is on your formula sheet. So it's P times what I call Q, or 1 minus P, over N. Again, put the numbers in, and you end up with 1.29. If you're not in the mood to draw the picture, you also could draw this. You can just say that the p-value is equal to the probability of p hat is greater than 0.2667, which is the same thing as the probability of z being greater than 1.29, which then returns the 0.098. Of course, you can also get that 0.098 using the table from the z-score or using the normal CDF in the calculator. Now that we have all these calculations done, what's our conclusion? Well, we see that our p-value of 0.0984 is larger than our alpha of 0.05, so we fail to reject the null hypothesis, and we do not have convincing evidence that more than 20% of the customers would pay $100 for the upgrade. Just a reminder, there are sort of kind of like 3 this or that options. We have larger, fail to reject, and do not have convincing evidence. But because we have 3 sort of kind of this or that options, that does not mean we have 3 decisions. Because the p-value is larger, we automatically fail to reject and then automatically do not have evidence. If the p-value was smaller than our alpha, then we would have rejected the null and then had convincing evidence. Next, let's talk about the errors. When I teach errors to my students, I put it forward like this. I draw this little diagram on the board. I say when they created the errors, they didn't try to make it hard. Our first hypothesis is the null hypothesis. The second hypothesis is the alternative. So when in reality the null hypothesis is true, but we error, that's a type 1 error. So let's read the type 1 error. In reality, only 20% of customers would pay for the upgrade, but the company incorrectly found evidence that more than 20% of the customers would pay for the upgrade. So as you can see, in reality the null hypothesis is true, but they erred and went to the alternative. For the type 2 error, that's when the second hypothesis or the alternative hypothesis is true, but we error and didn't have enough evidence to get there. So we can say that in reality, more than 20% of customers would pay for the upgrade, but the company was unable to find evidence to support this. So which error would be a more serious mistake? Well, the type 1 error is worse. The company would go ahead with the upgrade and lose money. But with the type 2 error, the company would only miss out on an opportunity to make money. So it would be worse for the company to lose money. Notice I made it very clear which is my answer. Type 1 is worse. And I also talked about the good of type 1, or really like the bad of type 1, and how type 2 is less bad. Whenever they ask for you to say which one, this or that, you should always say this one because that's the better choice, and not that one because that one is a worse choice. Address both. Lastly, let's describe 2 ways to increase the power of the test. Well, we could increase the sample size, and as we know, that's a good idea. Right? Whenever we can increase the sample size, that's going to decrease the variability, increase power, and reduce the likelihood of both errors, as long as you lower your alpha. And that's a great thing to do. It's a nice academic answer. It's not always plausible or cost efficient, but increasing the sample size will always reduce the errors and increase the power. Specifically, we're talking about decreasing the likelihood of a type 2 error, which increases power automatically. And then we could also increase the significance level, but it's generally not a good idea, because if you increase the significance level, that is single-handedly increasing the likelihood of a type 1 error. So yes, they both increase power, but increasing the significance level isn't a great thing to do necessarily. Don't fall victim to this good versus bad thing on a test. If I asked you what ways can increase power and you only tell me about sample size, that would be a problem. If this is a multiple choice test and I'm asking you about power, the choice with the larger alpha or the larger significance level is the answer, even though it's less desirable. So don't let that good versus bad mix you up. So I hope this has been a help as we talked about the 1 proportion z test, type 1 and type 2 error, and powers.